In this lesson, we are going to learn about graphing different rational functions. So, first of all, rational functions look something like this, where you have quantities in the numerator or the denominator. You need to know that a denominator of a fraction can never, ever, ever be 0. And so sometimes there will be places where rational functions are undefined. And one of the places that happens is when the denominator would be 0. So for instance, right here, if you think about what you would have to plug in for x to make that denominator be 0, negative 3 plus 3 would make 0, and obviously then x can't be negative 3 because then that fraction would be undefined. Sometimes you're going to get things that might look like this. 2x plus 3 equals 0, or 2x plus 3 is in the denominator, and sometimes people have a hard time figuring out what x can't be because it's not an easy number that you can plug in. Just go ahead and set it equal to 0, and then you would subtract 3 and divide by 2, and x couldn't be negative 3 halves there, just to tell you, okay? In this particular function, there are two things that x can't be. Obviously, if I plugged in a 1 right here, 1 minus 1 would be 0, and 0 times anything is still 0, so that can't happen. And then I can't plug in negative 4 here, or that would make this quantity be 0, and 0 times anything is 0. And then obviously I have this just plain old x here, and so there x can't be 0 either. So rational functions often have breaks in their continuity, which means that you can't draw that graph without having to lift up your pencil. So for instance, if I were to trace this graph, I would get here and here, and then I go, oh, got to lift up my pencil, which means that it's not continuous. Okay? If you can draw it without lifting up your pencil, it is continuous. If you have to lift up your pencil, it is not continuous. So they usually are discontinuous. Okay? There's some key things that we're going to look at. The first one is a vertical asymptote. What a vertical asymptote is it's sort of an imaginary line that the graph of the function will approach, and it will get microscopically close to it, but it will never, ever, ever touch it. So for instance, on this graph right here, it's not drawn in, but I can see that there's a vertical asymptote. So what happens is, from the right side, that line is going to positive infinity. From the left side, the line is going to negative infinity, but it gets microscopically close to that red dotted line and it never touches it. Okay? In this next graph, I have two vertical asymptotes, one here and one here. Notice that as you approach that line from the left or the right, the line always goes to either positive infinity or negative infinity. This is an example where this is a vertical asymptote here because the line approaches from the left, and from the right it goes to infinity or negative infinity. And then there's something called a slant asymptote. So this is a slant asymptote, which means that this graph is going to get microscopically close to that line as it goes to the right and as it goes to the left. But it's not a vertical asymptote, it's a slant asymptote. And we're not going to focus too much on slant asymptotes in this particular class. You'll hit that later, but just kind of know what that looks like, okay? And then there are horizontal asymptotes, which are horizontal lines that the graph would approach. And so that would be this imaginary line right here. And again, it won't be drawn in, and usually it should be dotted. Sorry, I should have made it dotted. But as you move off the graph from the left and the right side, the graph will get microscopically close to that line. So here my horizontal asymptote is at 0. Here my horizontal asymptote is, it looks like it's at about 1, but I can't quite tell. And then this graph here does not have a horizontal asymptote. There's no horizontal line that the graph approaches. You will find horizontal asymptotes with these rules right here. And we will talk more about these when we do an example, so I will do that for you in a minute. And then removable discontinuity is the name you use for when there's a hole in the graph, okay? and you figure that out by factors that cancel out when you simplify the function. And so all of this is just some background knowledge, and I think it will make a little bit more sense as we actually do these. So I'm going to talk about them with you in context, but just know that this front page of notes is super valuable to you, and you'll probably want to refer to that as you're doing some things because there's a lot of rules that you can get mixed up on pretty easily. Okay, so here is the whole, and there's a little bit more information here about how you find the whole. Again, it comes from factors that get canceled out, and then you can get the x value that way, and then you plug the x value in to get the y value. And again, I know this makes absolutely no sense until we actually do an example, but you can see pictures of holes right here. So there's a break in the action. Those are holes. And holes are called removable discontinuity. Okay? All right, so here we go. Hang on. All right, in this example here, we're going to look for the equations of any horizontal vertical asymptotes or any holes that we would have. Okay, so the first thing that you want to do when you do this is you want to simplify this function as much as you can, which means that you need to factor it. Okay, so when I factor this, the x squared minus 1 on the top we know is a perfect square, and it can factor as x plus 1 and x minus 1. And then on the bottom, the x squared minus 6x plus 5 can factor also, and that can be an x minus 1 and an x minus 5 is how that would factor. Okay, so what happens is this. I do have factors that cancel, and it's this one right here. When you have factors that cancel, they become a whole or removable discontinuity. Okay, so I'm just going to write this out for you in a lot of detail so that you remember this later. Holes or removable discontinuity. Okay, I'm going to just abbreviate that. Again, those come from factors that cancel. Okay, so the factor that canceled in this case is x minus 1. What you'll want to do is you'll want to set that equal to 0, and obviously we get x equals 1. So what I know is that I have a whole, and I know that the coordinate for the whole has an x value of 1. My goal is to figure out what's the y value of the whole. And the way you figure out the y value is you go back up to what's left, okay? So what's left after I factor the cancels, after I cancel the factors out, is x plus 1 over x minus 5. That's what's left. What I will do is I will plug this x value in, okay, to both of those spots, and I will get 1 plus 1 over 1 minus 5, which is 2 over negative 4, which becomes negative 1/2, okay? That will give me the y value of my whole. So my whole is at 1 and negative 1/2, okay? So that's where my whole is. Then my vertical asymptotes, I'm going to abbreviate that. My vertical asymptotes come from factors that remain in the denominator that would make the denominator be 0, okay? Factors remaining in the denominator. Okay? So what's left in the denominator after I cancel things out would be my x minus 5. So in this case, I would set x minus 5 equal to 0, and I get x equals 5. And x equals 5 happens to be a vertical line. I don't want you to tell me that my vertical asymptote is 5. I need you to write it as x equals 5 because vertical asymptotes are lines, and I need the equation of the line, okay? So make sure you give me the x equals. Then you have horizontal asymptotes, and horizontal asymptotes to do the horizontal asymptotes, you use the rules, okay? And by the rules, I mean these right here, and I know these are small, but you have them in your notes. But the rules about whether the degree of the numerator is bigger or smaller or whatever than the degree of the denominator, da-da-da-da-da. Okay, here's what you do. Go back to the original problem, okay? And you want to look for the highest degrees that you see in the numerator and the biggest degree that you see in the denominator. So the biggest degree, which is an exponent, that I see in the numerator is 2, and the biggest degree I see in the denominator is 2. So what that means is the degree of the numerator is the same as the degree of the denominator. And then what it says is that the horizontal asymptote will be the leading fraction. And you're going, I have no idea what you're talking about. Here's what you do. You take the coefficients of those terms. So the coefficient of this x squared happens to be a 1. The coefficient of this x squared happens to be a 1. I make a fraction out of that. And so my horizontal asymptote will be at 1 over 1. If this was a 2, it would be 2 over 1. If this was a 3, it would be 2 over 3. Okay? But I use my leading coefficients, which means it's the coefficient that's in front of the biggest exponent. So it's a 1 and a 1, and I make a fraction out of it. So in this case, it would be 1 over 1, which is just 1. Horizontal asymptotes, again, I don't want you to give me just a number. A horizontal asymptote is a line, so I want you to give me the equation of that line. Horizontal lines always have y equals equations, and so in this case, it would be y equals 1 over 1, or just y equals 1. Okay? So there's that one. All right, here's what we're going to do another one just to make sure you got this. So here we go. When we do this and we factor this, hopefully you can see that this will factor as x plus 2 and x minus 2. And the bottom will factor as x plus 2 and x plus 3. Okay? Sometimes you won't have anything that cancels, and then you won't have any wholes. Okay? So just know that that can happen. If nothing cancels out, then you have no removable discontinuity, just to tell you. In this case, the x plus 2's both cancel, which means I have removable discontinuity or a whole. I'm not going to write this out as much, but removable discontinuity. And it comes from the factors that cancel again. So x plus 2 cancels, so I would set that equal to 0, which means x equals negative 2. When you give me removable discontinuity, I need it as a coordinate, not just the x value. So I want you to give me the coordinate. So now I know that the x coordinate is negative 2. Okay? When I plug negative 2 back into what's left, I'm ignoring the part that's canceled. So what's left is x minus 2 over x plus 3. And when I plug negative 2 in here and in here, negative 2 minus 2 is negative 4. Negative 2 plus, this should have been a 3, sorry. And then negative 2 plus 3 is 1, okay? So I would get negative 4 over 1, which is just negative 4, okay? So I have a whole, or I have removable discontinuity at the point negative 2, negative 4, okay? So that's what that happens. All right, vertical asymptote. Again, vertical asymptotes come from the remainders, or the factors that remain in the denominator after you simplify. So this remains in the denominator. I will set that equal to 0. And of course, I would get x equals negative 3. Okay, horizontal asymptotes, again, come from the rules. Okay, so you're going to look at these exponents here. I have a 2 here and I have a 2 here. So the degree of my numerator is the same as the degree of my denominator. I will look at what factors are in front of it, which would be a 1 and a 1, and I make a fraction out of it. So 1 over 1 is 1. Okay, so I would just have y equals 1 right there. Okay, so that should get you started on this.